All right, so we'll get started with the first module of the course, which is essentially just introducing the scientific attitude, which is essentially how to think scientifically. In all of my modules and lectures, at least the first one in each module, I plan to lay out essentially what we're going to talk about through the whole module, but I'll just present it in the first lecture. For this particular one, my goal is to discuss scientific measurement and the elements of those scientific measurements. So that'll be this lecture, and then next time we'll actually talk about more of the philosophy of science, so scientific methods and what pseudoscience is. So the idea is that if you watched the course introduction video on Monday, then Wednesday would be this lecture covering 1.1, 1.2, and then Friday it'd be 1.3 through 1.6, just to give you an idea of the pacing for a Monday, Wednesday, Friday. So the only thing to note here is essentially measurements and observations are a hallmark of good science. And this is particularly in science, it's measurements and observations of the natural world. Okay, and this is what separates science from engineering. So engineering focuses on building things that interact with humans in the natural world, whereas science focuses more on the natural world itself. And something to point out is this one statement from the book, and we'll dive into this in depth, but how much you know about something is often related to how well you can measure it. Okay, and as an example of that, let's consider the planet Saturn. So the existence of Saturn has been known since like the 7th, 6th century BC by the Egyptians. Saturn was so obvious in the sky that they incorporated the position of it and other planets into a lot of their planning seasons and scheduling and things like that. So actually just looking here at this middle document, this is from a tomb, as you can see here. So this is on the ceiling of the tomb of, I'm gonna butcher this name, but I believe his name is Senenmut. And actually what's shown here are the planets and their names up here in the top left. So they knew about them, they knew that they wandered the skies, but they didn't know they were actually planets. Okay, so this is like our base knowledge and history of what planets are, is things that move in the sky. This even shows up in Egyptian religions, where the god Horus was associated with the planet Saturn. So this is Horus. He has the head of a bull or an ox, and typically in mythology, in Egyptian mythology, he's associated with the planet Saturn. Now, even back then, they knew that Saturn existed and moved around in the sky, but they didn't know that Saturn actually has a complicated ring system. And this is something we can see now just through an amateur telescope. You can see that here. By the way, if you download this, this is actually a video. You should be able to click and play once you download the lecture notes. If not, there's a link to this guy's YouTube channel if you wanted to watch this. If you're really interested in history, maybe you're a history major and you're taking this class as an elective, I do have several links throughout my lecture notes where you can click on it for extra tidbits of information. So if you do want to read about how the Egyptians sort of incorporated the planets into their religion, I do have this link here that you can download. So we go from the ancient Egyptians that knew that Saturn was a thing that wandered the sky, to something with a little more detail. We can zoom in now because we have a telescope. So actually Galileo was actually the first to observe Saturn with a telescope in 1610. Okay, so it's It's been quite a while since the ancient Egyptians were looking up at the planets and stars. So now we jump, 1,000 years or more. Um, Now we have the telescope, as specifically Galileo's telescope. So his telescope was essentially small and homemade, just doing the best he could with what he had. He was actually able to see Saturn as a planet through this homemade telescope. But what he couldn't do is he could not resolve the rings. So this is an important scientific term. So if you can't resolve something, it's kind of like, for those of you that wear glasses, it's like taking off your glasses and everything's a little blurry. For me, without my glasses, if I drive at night, two distinct car headlights in oncoming traffic, they just look like one bright light. I can't resolve both of them separately, two separate headlights on the same car. So the idea here with the word resolve and to resolve something in the sciences means you don't have enough information, or your instrument is not good enough to see more of the details. So because Galileo couldn't resolve the rings of Saturn, he just could see that there was something on the sides of Saturn. He just called them arms of some sort. And again, there's a whole history here on this link if you want to click it. But those arms that he was resolving, they actually looked like this. This is actually from Galileo's drawings in 1610 and 1616. So he knew there was something weird on the sides of this planet, but he didn't know what it was. So the problem was he was essentially limited due to the physics of his telescope. Okay, so the physics of his telescope would be like the lens geometry, whereas lenses were there's separation between them, because that's also important in optics, is the separation between optical pieces like lenses. So here's where the physics comes in. The physics of his instrument was not good enough to really get a good look at those rings. And you can see here, this is essentially the rudimentary telescope that he used. He's got two lenses here, and they're separated by some distance. And if you change those, change the size of them, change the distance, you can actually resolve more stuff. But just looking at his original telescopes, they're not that powerful. So let's move on from Galileo. We'll go up here to 1659. So we're still moving forward in time, and we're going to get to the Dutch physicist Christian Huygens. So he actually was able to identify these arms that Galileo originally drew like this. He was actually able to identify this as a disk around Saturn. Okay, so this was actually made possible by improvements in optics in Huygens telescopes. So here we can see this whole idea of, we're knowing more about Saturn because we can measure it better. Our physics is improving, our instruments are improving, so we're actually getting more information. So Huygens is actually able to resolve Saturn's largest moon, Titan. And here you can see, here's a picture, I think either taken by Voyager or Huygens probe. One of the NASA probes actually took this picture, and you can actually get a good view of Titan with Saturn in the backdrop. Okay, now we can keep moving forward in time. Okay, so now we're up here to 1675. So now we're looking at Jean-Dominique Cassini. He was a French Italian astronomer, and he actually discovered that Saturn's rings were not solid, but they at least had one gap in them. Okay, so again, more improvements in the physics and the instruments that's being used, so we can actually resolve more stuff about the thing we're studying. So Cassini was actually able to see that there was at least one gap in this ring, and nowadays, like this picture here is from NASA, and now we can send probes there and see that there's in fact lots of gaps in Saturn's ring system. So just to reiterate this idea, so overall the resolution of instruments increase with time. Okay, so as our resolution increases, so too does our knowledge. Okay, so there's sort of like if you were to think about it as a plot, it's sort of increasing like that. So we can sort of sum up what's going on here in this timeline. So if we think about back to 1610 with Galileo, we have a homemade telescope and we can see arms on Saturn. Okay, we can improve those optics. Then we can see a disk of Saturn. And then again, more improved optics. This is going to state-of-the-art optics at the time. We can actually see that these arms or this disk is actually rings. And then of course, we have so many NASA probes that are actually flying through the solar system, getting very, very high resolution data now. So generally the rule is as the instruments increase, so too does the knowledge. But as I pointed out here, great discoveries can still be made without state-of-the-art instruments. So an example of this I really want to point out, and this is from your textbook. It was a good read. I highly recommend you spend some time reading and thinking about this. But in general, scientific measurements involve three pieces of information: knowns, unknowns, and assumptions. And we're going to think about this in terms of Eratosthenes, who actually very accurately measured the circumference of the Earth, like very accurately, pretty much just using some prior knowledge and a yardstick or a meter stick, just a small measuring device. Just using that and very careful assumptions, he did a really good job measuring the circumference of the Earth. So let's talk about how he did that. And I'm going to do just a quick time check. Okay. So Eratosthenes pretty much used known information, simplifying assumptions, and gathered unknown information to create this nice packaged fact about the Earth, which would be its circumference. He was one of the first librarians in Alexandria, Egypt, so he had a lot of time to go through and read information. So as far as knowns, what he did know when he was trying to calculate the circumference of the Earth, he knew that the sun is highest in the sky at noon on the summer solstice. Okay, that's the longest day of the year. That's when the sun, no matter where you're at on Earth, that's the point it's going to be the highest for wherever you're at. So at this time, a vertical stick would cast the shortest shadow. Totally makes sense. So you can imagine if your stick is here, your sun rays are coming in, you're going to have the shortest shadow length right there on the summer solstice. Now, if the sun is directly overhead, you won't have a shadow. So that's if the rays are coming down, there's nothing there to actually cause a shadow. This is what he knew. This was common sense. What he did not know, some unknowns that he needed, he actually had to do some research. Now, this technically would be more of like what scientists would call a literature review. So he, quote unquote, did his research or literature review and went through all of the literature in the library that he was running. And he found that the sun was actually directly overhead at noon on the summer solstice in another city, which is now Aswan in Egypt. And it's actually just south of Alexandria. So here's what we're looking at. he's up here in north, near Cairo, up there in the Nile Delta. But he knew from literature, someone had written it down, that it just so happens the sun shines directly straight down a well, like a water well. So the sun shines directly down a water well. There's no shadows on the sides on the summer solstice down here in this southern city. Okay, so he took care of his unknowns, the things he didn't know. Now he needed to make some assumptions. So he pretty much reasoned that if the sun's rays were extended into the center of the Earth at noon on the solstice, they would pass through its center. So ideally, if this is the side of the Earth, sun's rays are coming in. Okay, that sun ray, since it's coming straight in the well, so here's the well, that's going to essentially go through the center of the Earth. And then he used the same idea. If he set up a vertical stick at Alexandria to the north, okay, there's his vertical stick. If he set up a vertical stick, but he could imaginarily extend it, that would also have to go through the center of the Earth. Okay? So his assumptions are that the Earth is perfectly spherical. We know today it's not, but that's the only way this assumption is going to work, is that the Earth is perfectly spherical. The other thing he assumed is that the sun's incoming rays are parallel. So he's assuming all the rays coming in are essentially parallel, which is not a bad assumption to make. Okay, so when the time finally came, when the summer solstice happened, Eratosthenes measured an angle of 7.2 degrees between the incoming sun rays and a pillar in Alexandria. Okay, he then measured the length of the shadow that was cast. So just as a quick idea, here's a pillar, okay, a sun rays coming in. So he measured two things. I'm going to try to do this in a different color. So he measured this angle here. I'm going to draw it in green. So he measured that angle. And in physics, we usually call those Greek letter theta, a circle with a line through it. So he measured that angle. And then he also measured the length of the shadow that was cast down here. We can call that L. Okay, so there's my simple picture up top. Here's a slightly more complicated picture. There's a lot going on, so let's take a minute. Okay, so here in green is this pillar, and it's labeled there that 7.2. That's the angle between the sun ray coming in and his and the pillar itself. And you can see this also shows the imaginary axes he drew going into the center of the Earth. You can also see the well down here and the imaginary line coming in going to the center of the Earth. Okay, now let's really break down this bottom image. So we have the incoming parallel sunbeams. Those are in purple. On the summer solstice, these beams travel straight down the well. Okay, so we can see that here. So clearly this image was taken on they're drawn for the summer solstice. The axis of the vertical pillar, okay, we already talked about, is assumed to intersect at the center of the Earth. And then the distance between the two cities, that was well known, because there were very popular trade routes that were pretty direct, and they knew it was stadias, I think, is the units that they use. So many stadias, but this is going to be in kilometers, so the distance is about 800 kilometers. Okay, so we got that labeled here, the 800 kilometers. Okay, now let's zoom in to see what's going on. Okay, so you'll notice my big red dotted arrows just showing that we've zoomed in. And here is Eratosthenes standing on the side of the Earth, right? Because his head's facing this way toward the sun. And this is essentially what we're looking at. So we have this angle here he measured. Okay, that was the 7.2 degrees. The height of the pillar was 8. We can call it meters. It doesn't matter. I'll say it's 8 meters, and then he measured a 1 meter shadow. Okay. Okay, so he's got the 7.2 degrees. Now, what does he do with that measurement? Okay, well, he used Euclid's fifth axiom of geometry. And the idea here is that if you have two parallel lines, like we do here, so we have two parallel lines. Any two parallel lines, if you intersect them, or just draw a line across them like this, you're guaranteed to have two of the same sized angles. So this angle here, this theta and this theta, these will be the same. Okay, so he knew this and he wanted to use this, and he needed it. He didn't want to use it, he had to use it in his calculation. Okay, so here in this case, these black lines, these black parallel lines coming in, these are actually sunbeams coming in. And then this line here, the dotted line, that dotted line is essentially the axis going to the pillar. That imaginary axis going to the center of the Earth. Okay, so using this imaginary line, he knew that the angle made by the cities themselves was also 7.2 degrees. So he essentially took this, moved it down to his drawing, and then he knew, well, if I measured this angle here, I'm going to try and draw that in blue. If I measured that angle to be 7.2 degrees between an incoming sunbeam and a pillar, then the angle here between the cities, using Euclid's fifth axiom, the angle here has to be the same, also 7.2 degrees. Okay, so the angle between the two cities is 7.2 degrees. Well, that's just a piece of a full circle around the Earth. You can see that down here in the bottom picture here, right? So I'm going to draw it in. This 7.2 degrees, that's just a slice of the full pie of the Earth. Okay, so this 360 degrees, that's a full circle. So his logic was, well, if this little piece here in purple swept out between the cities is 7.2 degrees and a full circle is 360 degrees, well, that means this is just 1/50th of a full circle, or roughly 2%. So the distance between these two cities, Alexandria and Cyan, this was 2% of the entire circumference of the Earth. Okay, so, or 1/50th, which means 50 chunks of this added together would give you the circumference of the Earth. Okay, so if it's that one distance is 800 kilometers, okay, that's 2% or 1/50th. So 50 of those would get you all the way around the Earth, and that turns out the circumference will be about 40,000 kilometers. Okay. So how accurate was Eratosthenes' calculated value of 40,000 kilometers? Well, the accepted value of the Earth's circumference is about 40,070 kilometers. Okay, this is due to the fact that the Earth is not a perfect sphere, but look at how close he was. That is a percent error of 0.2. That's less than being off by 1%. It's a fraction of a percent. And that's just using some logic and a measuring device. So he had this awesome value. He knew the circumference of the Earth. Now what he could do is he could push this further and say, well, I have this information. How can I squeeze out as much science as I can? So moving forward, he's like, well, I have the circumference. I could actually figure out the radius or the diameter of the Earth. Okay, so using the fact that the circumference of a circle is 2 pi r, you could actually divide the circumference by 2 pi, and that would actually give you the radius of the Earth. Okay, so that happened here, and it turns out from his calculations, he could determine that the radius of the Earth was 6,367 kilometers. Okay, now this, I want to reiterate again, he figured this out using a tall pillar and a meter stick. Okay, that's really impressive. Take a moment and let that sink in. Now, the last thing I want to talk about is just a quick aside to answer the question, how exactly did he measure that angle? So hopefully you guys remember from high school, your trig functions. So there's the old saying that the SOHCAHTOA. So if it's a sine, so, which is going to be opposite over hypotenuse, a cosine would be adjacent over hypotenuse, and then tangent would be opposite over adjacent. Okay, so there's your SOHCAHTOA. It's a good way to remember it. But the whole idea is any angle here, so we'll look at sine for the moment, any angle theta in a triangle, so like this angle down here, so any angle that's going to be related to the lengths of the other sides of the triangle. Okay, so here, like with sine, okay, and then we have this angle, so it's this angle is related to the length, the opposite side here, and the hypotenuse here. So if we know the length of those sides, we can get information about the angle. If we know information about the angle, we can get information about the length of those sides, because they do form a ratio. Okay, now let's take a look at this setup here that Eratosthenes had. So he knew he wanted an angle. That's the thing he was after. He wanted an angle of some sort. So we're solving for theta because we don't know it. It's right here. But he had information about the sides. So he knew the adjacent piece, because that's the piece touching his angle. That's not the hypotenuse. The hypotenuse is always the longest side. So he knew the adjacent piece and he knew the opposite piece. Okay, so it looks like tangent's going to be our best bet because there's opposite and there's adjacent. Okay, so in this case, we have the opposite side being the shadow, the adjacent piece being the pillar, and we know what the lengths are. Since we're looking at the ratio, we don't care if it's feet, meters, yards, no one cares, because it's the same unit in the numerator and the same unit in the denominator. Okay, so these are just going to cancel anyways. So we know the shadow has a length of 1, we know the pillar has a length of 8, and that leaves us with tangent of theta is just 1/8. Okay, so now the question is, how can we use that? We have this relationship now, but we want to get theta by itself. And we simply just take the inverse of both sides, just like solving any other equation. So we're trying to get tangent out of here. Well, let's take the inverse tangent of both sides, because it's an equation. Whatever you do on one side, do on the other, okay? So we're going to take the inverse tangent of both sides. If you need to do this in this course, you can actually just type in inverse tangent of some number in like a Google search, and it should spit out the answer. Okay, so we do that. What happens here is these tangents cancel each other out. We're just left with theta, but then we have to take the inverse tangent of 1/8. So if you do this, remember the whole thing from high school, degree mode versus radian mode. So make sure you're in the right mode. So here you want to make sure you do this calculation in degrees. Otherwise, you'll get the right answer, but the wrong units. Okay, so when we do this, turns out we get approximately 7.2 degrees, and that's sort of the approach that Eratosthenes used to figure out that angle. All right, so we'll stop here. The next lecture, we'll actually start talking about scientific methods and that scientific attitude. But for now, read the associated sections in the textbook. It actually goes through a few more calculations other than just the circumference of the Earth. I believe it covers the distance and size of the sun, distance to, and size of the moon as well.